So now we're going to talk about upward lightning, and this has been my focus of study over the last 20 plus years. And again, to define upward lightning, it is the development of an upward propagating leader from an object that's attached to the ground. It can be either man-made, such as a tower, building, or any structure that enhances the electric field locally, but it also can be a naturally occurring object, such as a rock formation, a steep rock formation. We've seen upward lightning occur from mountain peaks, rock formations in both the Canyonlands National Park, Shiprock. Um, we documented an upward flash captured, or multiple upward flashes captured by Jim Tang, storm chaser there, that was there and saw multiple upward flashes from Shiprock. So it can be both naturally occurring, man-made, because there are so many towers that have been built, wind turbines, tall buildings and such. We more typically see them from man-made objects. But this is what they look like. They are most commonly, by far, positive leaders that develop upward from these structures. And they have upward branching, which indicates their direction of motion is upward. We see it obviously with the high-speed cameras. Their actual physical movement is upward. Given that they're positive leaders, and if they branch, we'll almost always see recoil leader activity, so they can be prolific recoil leader producing. And this is a lot of how we studied and learned recoil leader activity and behavior, was due to upward flashes, where we were able to see this positive leader activity so clearly below cloud base. We were able to capture, analyze that behavior, and learned a lot about recoil leaders. So these are towers, television towers in Rapid City. They're just under 200 meters tall. And you'll notice that we had a bright main channel, and these channels kind of fade out, intensify as the leader encounters different areas of cloud charge, and then branches decay and redevelop with recoil leader activity throughout the flash. Here's another example of 1,000 images per second. So what we've learned, and the whole reason we focused, now upward lightning has been observed for a very long time. It has been studied going back to the 1930s. Empire State Building was used as a platform to study research upward lightning back in the 30s. So this is nothing new. We know about upward lightning. We understand that it occurs. What I try to focus on is to try to really quantify what causes upward lightning, the physical mechanism behind that initiation and develop of upward lightning, and try to better characterize that process. And we learned that nearby flash activity is a primary trigger of upward lightning from nearby tall objects. So there has to be a naturally occurring flash that takes place, and a component of that flash influences the electric field around that tall object, and that results in the initiation of an upward positive leader, in most cases from those tall towers. And we call that lightning triggered upward lightning. And so we'll take a look at the various mechanisms of which that occur. And the first of these is just a nearby IC flash. And the normal scenario, again, is if we have these horizontally extensive storms, if the trailing stratiform precipitation area is over those towers, those are the favorable conditions for upward lightning. So you have this horizontally extensive positive charge region and a screening layer, maybe some negatively charged rain that's falling below cloud base. We see negative leaders propagate over or near the towers, and that creates a field change that results in the initiation of upward positive leaders. So this first one looks at just as an IC, an intercloud flash, in which negative leaders are brought over the towers and upward positive leaders are initiated. As you can see, as that progresses spatially closer and closer to the tower, that initiates the upward positive leader first from the closer tower, and as those leaders continue to move over the second tower, we get the second one developed. And during our study, the upward lightning triggering study that took place in Rapid City in the years around that time frame, we involved multiple instrumentation, as I showed, the fast antenna, slow antenna, electric field meters, and lightning mapping array. And here is an example of that particular mechanism where we have an IC flash that triggers an upward leader. And what you're looking at here is, here's the high-speed recording that'll be recording the upward leader and the previous flash activity. And what we see in the fast antenna, so this is primarily around the zero value, but then it records fast changes in the electric field as they occur. And as you see positive excursions or positive field change, it's due to negative leader activity overhead. And so we're seeing a positive change due to that negative leader activity. And in this case, if we then look at the LMA, this is a top-down view of the LMA, which again maps the progression of leader activity in 3 dimensions, with the rainbow using rainbow coloring as time versus altitude. This is a top-down view. And then if I were standing south of that flash looking north, this would be the view I would have in terms of altitude and left to right, if you will, as I'm looking, or east-west as I'm looking at it. If I was standing west of this flash looking east, I would see this view, and this would be north-south, and then the altitude would be in this direction. So let's take a look at this and see how this flash progresses. So we start seeing field change, and that is a result of negative leaders in cloud during an IC flash. Here's the positive leaders associated with that. And that results in upward positive leaders. They're rather faint, but they are there. They're producing recoil leaders. That results in upward positive leaders initiating from these towers. If we look at the time scale of that, here's the propagation. This is where the towers are. And the leader activity, the blue portion, passed over that tower, and there was more development away from that tower. And when those negative leaders passed over those tower, according to the LMA, corresponded to the electric field change and the initiation of the upward positive leader. The other way previous flash activity can trigger upward positive leaders is through a return stroke. Now, previously we just showed the negative leader activity from the IC flash go over the towers. But in this case, negative leaders may propagate towards or near the towers, but the field change isn't enough to initiate upward positive leaders from those towers. So we don't see triggering even though those leaders moved overhead. But then there's a return stroke and a rapid intensification of this leader network in the negative sense that occurs due to the return stroke. And that electric field change that we experience is actually the mechanism that triggers the upward positive leader and from both the towers. In this case, it's going to happen more in a simultaneous manner due to the intensity of the return stroke field change. So no leaders, but now that we have the return stroke travels throughout the leader network, and it's that return stroke that triggers the upward positive leaders. And we can see this visually. Here's the triggering positive CG return stroke and the response from the tower from that return stroke. And again, here's another one. In this case, the return stroke occurs off the field of view to 90 kiloamp positive CG return stroke. So previous negative leader activity, this does not initiate any upward leader activity, but that return stroke clearly triggers that intense upward leader, positive leader growth. And one more example. Positive leaders coming down. Return stroke. And upward positive leader in response. So the third way in which we can trigger upward leaders from the towers is we still have a positive CG return stroke, but the return stroke is either too far away or not strong enough, and or the previous leader activity isn't positioned close enough to the towers that return stroke itself does not trigger the upward leader from the tower. But following the return stroke, we get intensified growth, continued growth of the negative leader portion of that flash, which results in a continuing current, as we talked about. And that growth, subsequent to the return stroke, travels near or over the towers, and that initiates the upward positive leaders from the towers. Again, beginning of our bidirectional, there's the return stroke, but it does not trigger the upward leaders. It's the growth after the return stroke as they spatially travel over the towers. And again, typically you'll see the closer tower initiate first as the post return stroke negative leader extension moves closer to and over the towers. So in the first case we saw it was just negative leaders. The second case it was the return stroke. And in the third case there is a return stroke, but it's the negative leader growth and extension following the return stroke that triggers the upward positive leaders. And we'll take a look at that one, this type of mechanism again, using the electric field change and the lightning mapping array display. And here's the towers that are going to initiate upward positive leaders. Here's the positive CG return stroke location. We'll see the negative leaders in cloud. And looking at the electric field change, the return stroke is indicated by this very sharp electric field change recorded by the system, but that does not initiate the upward leaders. It's this growth afterward, this field change here, that results from the negative leaders that continue to grow and expand, and they move spatially over the towers, and that is what triggers the upward positive leaders. So, return stroke, no upward positive leaders yet. This is where the negative leaders then travel over the top of the towers. Following return stroke, we see the continuing current continues, and that is what initiates the upward positive leaders from the towers. And looking at the LMA display, the CG again was in this location, but it was the subsequent growth following the return stroke that moved over the towers, and the towers are right here. That spatial dependence is what resulted in the upward positive leaders developing. Here's another example. Turn stroke, no response from the towers yet. Here comes the negative leaders following that return stroke, resulting in the continuing current. And now, as the farthest northmost tower initiates an upper positive leader, a tower further south, as the leaders move towards the camera, closer to this tower is closer to the camera, that initiates secondarily. Well, we've obviously seen cases in which multiple towers can initiate upper positive leaders in a single flash. This is one of the most spectacular upward lightning flashes that I've witnessed during my uplights campaign. And in this case, there was 9 towers that initiated upward positive leaders. You can see 1, 2, 3, 4, 5. There's another one that's quite faint, 6. In this field of view there, and there's more other towers. So this is the triggering positive CG return stroke, and these are the subsequent response. We'll take a look at this in real time. And lit up the whole sky. So now we're going to look at another type of upward lightning, and that is self-initiated upward lightning. We looked at how nearby lightning activity can trigger upward lightning from tall objects. That's lightning-triggered upward lightning. But this is self-initiated upward lightning. There's no nearby preceding lightning activity that causes this upward leader to develop. It just initiates on its own. And what is the mechanism behind that? Well, in order for that to happen, you have to have a very intense electric field that it now allows for self-initiation and self-propagation of that upward leader. And that occurs in a more intense electric field environment. And we typically see this more so in winter environments where you have blizzards, snowstorms, that are very energetic, that also become electrified due to their intensity and thermodynamic profiles and the microphysical situation, such that you get this cloud charge that's actually much closer to the tip of the tower. And in some cases, the tower itself is actually in the cloud charge region. It's above cloud base, and therefore in the cloud charge. And so you get this very intense electric field, and then you get the initiation of an upper propagation leader. Something that can help that process is wind over the tower tip. And the reason for that is when you put a conductive object in a electric field region, we've seen that corona brush that can develop, that corona, that point discharge. And in the case if it's a positively charged tower due to nearby negative charge, you can create corona ions due to that streamer activity, and those are positively charged, and they act as a shield. They're kind of shielding the negative charge's influence on the tower tip because they're the same polarity as the tower. You have a positive tower, positive ions, and therefore they are shielding the tip somewhat from that negative charge region, and the electric field is reduced. So it's a shielding process that's naturally produced to the corona or point discharge. But if you have wind and you take those corona ions away, it exposes the tower tip to that full electric field. And that is a condition that we think aids in the initiation of a self-sustaining upward propagating leader with self-initiated upward lightning. And so the times that I have observed self-initiated upward lightning here in Rapid City, it's only been due during intense winter storms with heavy snow, low cloud base, and very strong winds. And that's the only time that they have initiated, been self-initiated. So let's look at that. Again, you have a negative charge region that's down close to the tower tip, resulting in the tower positively charging due to induction and the eventual development of an upward positive leader that spreads out into that negative charge region. And what we see during these thunderstorms or these winter storms is that charge region can be pretty extensive horizontally, and that these flashes can last for a very long duration with multiple leader directions and activity, and the resulting flash is a long duration upward self-initiated upward lightning flash. And we were actually able to record this process here in Rapid City during the Uplights campaign. Excuse me. We had a digital interferometer, which, like a lightning mapping array, is able to detect the emissions from leaders as they develop. In this case, this was a two-dimensional interferometer that uses those emissions. It's not a time of arrival. It uses a different phase alignment from the received emissions to detect the direction from which they're coming and the timing of that. But we were able to detect during a winter storm in 2013 the development of upward lightning from the towers in Rapid City. And what we'll see is that sure enough, the sources are originating from the tower tip and expanding upward and growing and branching upward, just like we see in normal upward lightning. The towers were not visible. The blizzard had visibility, less than just a few hundred feet at best. Winds were howling, and it was a very intense storm. And so we captured 5 upward flashes from the towers before we lost power to the region, and were able to document this. And in this particular case that I'm going to show you, one of the positive leader branches that continues to grow outward starts producing recoil leaders that positive leaders typically do. And one of those recoil leaders, the negative end, comes back towards the flash origin or the tower, but then again jumps the track, starts stepping to ground, and connects to ground away from the tower, and causes a negative CG return stroke along that branch. So kind of that hybrid scenario where a component of a previous flash generates a secondary flash. And what's interesting about this, if you think about it, this was a flash initiated from the ground and then resulted in another ground flash nearby. So literally this is a ground to ground lightning flash, not a cloud to ground, not a ground to cloud like more normal upward lightning is, but a ground to ground. It did grow up towards the cloud, and the first component was ground to cloud, but then there was another component that developed and went back to ground. So literally a ground to ground lightning flash. So let's take a look at that as that develops. So there's the development. We're starting to register recoil leader or dart leader return stroke sequences and the positive leaders at the tower location, and these show up here as negative CGs since the negative end is connecting to the tower. And the flash continues to grow, and then all the way out here we'll start seeing an attempt to come to ground, and finally it does come to ground. So subsequent recoil leader development with a negative end finally coming to ground and causing a negative CG away from the tower itself. And here's the actual video recording from my terrace, my observatory at my house during this storm, during this event. And you can see the visibility was minimal, but you can hear the thunder that occurs resulting from an upward lightning flash from the towers. The towers are about, from my location, about 7 kilometers away. There's the flash. Just notice how long this lasts. So now we're going to get into wind turbines and their experience of upward lightning, because wind turbines can be prolific upward lightning producing objects. They're elevated. They can be spinning, and so we talked about the wind as a way of exposing that tower tip as it builds up corona charge. It allows it to move away from that shielding corona charge that's generated. And again, a lot of our focus during our research was to try to understand the triggering mechanism, exactly how upward lightning flashes occur physically, the weather conditions that are favorable for those types of flashes, and we've already shown that mesoscale convective systems in the trailing stratiform precipitation area is the most favorable area and type of storm to cause upward lightning from tall objects. And this is a very important issue for the wind power industry. They want to know when their turbines are more susceptible to lightning attachment or initiation, as well as the type of damage that occur during lightning. They do have lightning protection systems on wind turbines, but they still can experience damage. So why is that? Is it attaching at the locations that it should based on the lightning protection system, or is there another mechanism that's resulting in it not utilizing that lightning protection pathway? And so that was also the focus of our studies as we accomplished these observations. And so here's an example of what it looks like when a wind turbine gets struck. You'll see that it initiates when the turbine is at a certain location. The same triggering mechanisms that I've talked about, flash components, all those are the same. But what's different about wind turbines is that the attachment point can be dragged along as the wind turbine blade moves during the flash. And here's an example of a upward leader flash in which multiple wind turbines initiate upward positive leaders. This is one particular flash in which we have numerous wind turbines generating upward positive leaders in a single flash. So this is all during the same flash. There's a preceding negative leader in cloud, and in response we see all these wind turbines initiate upward positive leaders. And obviously a very long duration flash as well, as some of these upward leaders exhibited multiple dart leader return stroke sequences. And you can imagine that this wind turbine is again experiencing multiple impulsive current events to its blade tip. Here's a dash cam standard speed camera showing the process. You can see how it drags the channel along the pathway as the blade moves, and then eventually cuts off and leaves behind kind of a glowing arc, some of which may linger for a while if it's metal or something is actually burned off. Another example involving multiple power or wind turbines. Fortunately, most standard speed cameras have a rolling shutter, so you see this artifacting due to the rolling shutter. So now let's look at this with high-speed imagery. Again, here's this same multi-upward leader flash that I showed earlier in a still image, the digital still image. Preceding flash, negative leader activity overhead, causing this brightening, and then a response from the turbine blades. See the corona brush on the positive leaders. Notice how the closer ones initiated first, further ones secondarily as the leaders passed overhead. Another upward flash, again showing how the channel can be dragged along by the tip of the blade as it rotates before decaying. And one thing that we observed, which was quite interesting, is that you can have attachment occur to a particular blade, and then that channel again is dragged along the arc, but we can see decay in that first attachment, and then you may get dart leader return stroke sequences along the decayed channel pathway. But we actually saw that one of the dart leaders or subsequent dart leaders came down and did not travel along that arc and reattach to the tip of the original blade, but attached to a subsequent blade as it rose up during the flash, and actually attached to a secondary blade. And we've only captured this a couple times. It was quite a far distance, so I've cropped this intensely, and hence the poor resolution. We see the blade rotate and its associated attachment still. It decays. And it actually travels quite an extensive arc. It's rare to see it go that far. Then the subsequent attaches there to the uprising blade 2 times. Three times. So now we better understand upward lightning. We're going to kind of relook at horizontally extensive thunderstorms and their flashes and see how that they can contribute to transient luminous events, or some of the transient luminous events that only show up when we have horizontally extensive flashes.